Hey everyone, my name is Gowtham Seenivasaharagavan and I'm a grad student at UC Santa Barbara. Today I'm going to be talking about the effect of mean subtraction on dynamic mode decomposition. This is joint work with my advisor Igor Message and my mentors Milan Korda and Hassan Arbagi. We're looking at discrete time autonomous dynamical systems and we're going to analyze them using the Koopman operator. Koopman operator takes functions in the state space and maps them to composition with the flow map. Uh, this is typically an infinite dimensional operator, but it's linear, so you can ask for its eigenfunctions and eigenvalues if they exist. If you can find these spectral objects, you can say something meaningful about the system. So naturally, you like to approximate this operator, and a popular algorithm to do that is dynamic mode decomposition. So here you choose a set of observables that you're interested in, and then you try to approximate the image of each observable in the span of the observables themselves. This ends up being a linear regression problem where you have two matrices, one being the samples of the observables at sample points, and the other being the image of the observables at the same sample points. Now, if your data is from a single trajectory, you can alternatively try to find the A that best that has X as an invariant subspace. And so the resulting optimization problem takes this form where you're trying to predict the final snapshot as a linear combination of the previous snapshots. An important parameter here is n, which is the number of columns of X. It is also the order of the DMD model. Once you have C star, you can use it to find its spectral decomposition, and then use this to decompose your time series as a sum of vectors that grow or decay according to these values here. So Tj star are the Ritz vectors, and they're also the approximations to the Koopman modes, while lambda j star are the Ritz values, and they are the approximation to the Koopman eigenvalues. Now, the utility of this expansion is that it helps you understand the physics behind complicated systems like fluid flows. And people eventually wanted to make reduced order models with this decomposition. And one thing they wanted was for the model to preserve boundary conditions. Now, in its essence, this problem is asking if the snapshot satisfy this relation, does the prediction of the model satisfy the same relation? And one way to achieve this is by subtracting the mean. So let's say Zi are my snapshots and mu is the temporal mean. And these are your original data matrices. Then subtracting the mean gives you the mean subtracted matrices. And mean subtracted DMD is just doing companion DMD on these matrices. So you can show that if you build a predictor like this using the mean subtracted C, then that prediction will satisfy boundary conditions of a specific type. So this is good, but there's a potential pitfall to this. If the mean subtracted X has full column rank, then CMS is restricted to be a column of negative ones, which is equivalent to saying the Ritz values are n+1 roots of unity. So this is saying that if and the situation is called spectral equivalence to TFT. So what this means is that if this rank condition holds, then regardless of the underlying system, the Ritz values are going to be on the unit circle. Now, this work here by Hirsch and co-workers, they pointed out that this is a sufficiency condition and that this rank condition doesn't always hold when you have data from a finite invariant subspace. To be specific, we're going to assume that you have R distinct eigenvalue eigenfunction pairs. We can assume that our observables lie in the span of these eigenfunctions. So the eigenfunctions evolve like this, and our observables are a linear combination of our eigenfunctions. Under this setting, you can show that having a trajectory that is having a model order that is long enough, that is large enough, is enough to ensure XMS doesn't have full column rank. And so this is kind of clarifying the role of this theorem, but which is good, but it's not equivalent to showing a necessary condition for spectral equivalence. So what we do is find a necessary and sufficient condition for spectral equivalence of DMD and DFT, and then we use this to say something about the model order. So if the order of your model is strictly more than the dimension of the invariant subspace, then there's no spectral equivalence. If your observables are good enough, then n less than r means you will have an equivalence of mean subtracted DMD and DFT. And when n is r, an edge case depending on whether or not you have one in the spectrum of your spectrum of lambda. Numerically, so this condition here, you can always meet it by taking sufficient delays. And this condition is equivalent to measuring the norm of the distance between CMS and -1n. So what you can do is the following. You can take a trajectory and you can compute this quantity for different values of n. And then you can repeat this experiment for an increasing number of delays to check if the trend remains the same as theory predicts it should be. And then you can repeat this whole setup for a lot of trajectories and do some statistics on it. So first system that we're looking at is this simple LTI system where all the eigenvalues are on the unit circle. And the x-axis is n, the magenta line indicates r, which in this case is 7, and the y-axis is an indicator of the deviation from spectral equivalence. So when n is less than r, you have spectral equivalence, and when n is more than r, you don't have. Same thing here, and there's an edge case. Now, when you add some eigenvalues that are within the unit disk, you get a similar trend, only that the transients are much better now. The next example is one where you don't have a handle on what your dictionary is precisely doing. So here, set of observables you're choosing are just the state variables for the van der Waals oscillator. And what you see here is that the transition from spectral equivalence to not depends on number of delays you take. And if you look at the largest number of delays taken, you see there's no jump indicating departure from spectral equivalence. So this is the same as saying this choice of observables doesn't lie in a finite dimensional invariant subspace of dimension less than 20. Last example is the lid-driven cavity at Reynolds number 13,000, where you have a limit cycle, and here the pattern matches theory. So you can either be optimistic and say you have a finite invariant subspace, or it could be the fact that your observables are particularly bad for the system, and which is in truth much higher dimension. So to summarize, if you believe your observables lie in a finite invariant subspace, equivalence of DMD and DFT implies you need to collect more data. If you don't have an equivalence of DMD and DFT, and this persists as you take more and more delays, then you have enough data and you can do companion DMD and trust what you get out of the modes. Thank you for listening to my talk.